Hi everybody, it's time for video 3 of lecture module 4. We have now ended our discussion about the Earth and are moving into part 4 of unit 2 about the moon. So let's go ahead and get things started right here. And we are now talking about celestial objects other than the Earth in the solar system. This is sort of the beginning of our tour of the solar system. I want to go ahead and show a couple of pictures of the moon just to show you a couple of the basic concepts that are going on. So yes, we have put people on the moon. Here's a nice picture of some astronauts to the moon, their little moon buggy. We got some mountains in the background. You can see that the surface is covered with like this fine-grained powder of rock, which we call regolith. If you take a look at the moon as a whole, you can see that it has craters all over the surface. It also has these darker areas, the lunar maria. And then if you were to zoom in on these areas here, they would be cratered and look like mountains. They have a higher elevation as well, so we call them the cratered highlands. Interesting overlay on all that is if we want to look at the amount of iron that's on the surface, things that we expect to be deeper down in, looks like where all these dark areas are, they're also enriched with iron, almost as if some subsurface material has been brought to the surface. This is the side of the moon that we're used to, the near side. Here's the far side. Pretty different, pretty different. So with every celestial body that we'll go through, I run through what I call the basics. I know this looks like a lot of boring material, but really this sort of sets the stage for understanding a planetary body. If you have a deep knowledge of planetary science and planetary astronomy, then you can go and look at the basic data of something and tell a whole lot about it. I'm not going to have you memorize all of these numbers, so don't worry about that. The things I would like you to remember are really highlighted in blue. Notice I'm not even going to ask you to remember how far away is the moon. You should have a rough idea, or at least I'd hope that you would after this class. But the distance, the average distance between the Earth and the moon is 384,400 kilometers. Kind of a fun way to think about it is if you put every other planet in the solar system end to end between the Earth and the moon, that would stretch almost the exact Earth-Moon distance. So pretty much you can squeeze every planet in the solar system between the Earth and the moon with only a little bit of wiggle room left. How big is the moon? The moon is not very large compared to the Earth. It only has a radius of 1,738. Remember, the Earth was 6,378. That gives it an overall radius, kind of put things into perspective. It's always helpful to consider things relative to something that we understand. The Earth is 27% the radius of the Earth, or you could say it has a radius of 0.27 Earth radii. What is the mass? It's about 10 to the 22 kilograms, 7.3 times 10 to the 22 kilograms to be more precise, which ends up being about an eighth the mass of the Earth. So it has about 1/8 the total mass of the Earth. Now this ends up being a very interesting number. The average density, and density is just how much mass you have per volume. So how much stuff you have crammed into a space. The average density of the moon is 3,300 kilograms per cubic meter. Earth is about 5,500 kilograms per cubic meter, so a lower average density than the Earth. But then, what is a useful thing to do? And we have samples of moon rocks from the surface of the moon because we sent astronauts there, and a lot of them collected lunar samples, returned them to Earth, over 400 kilograms of lunar material from the surface. So we know the density of the rocks on the lunar surface quite well. And they come in at 2,500 to 2,800 kilograms per cubic meter. So the surface material is less dense than the average material, the average density of the moon. What does that tell me? Well, if the average is higher than what I see on the surface, then deep down within the moon's interior, I must have higher density material to bring the average to equal 3,300. And what do we call it whenever we have the dense stuff in the inner regions and then the less dense stuff in the outer regions? Oh, instantly I can tell that the moon is differentiated. Just by examining the density of the surface rocks compared to the average density tells me that there has to be more dense material than the average in the interior. Just fun things to think about. The surface gravity is 1.62 meters per second squared. That doesn't mean a whole lot to you. So that puts at about 1/6 Earth's gravity, about 1/6 G, about 17 or 0.17 G, 17% Earth's gravity. So yes, you can jump high on the moon. And in fact, this low surface gravity made it really kind of hard for the astronauts to move around on the moon. They tried by just starting to walk like regular people, because, you know, that's how we walk. They fell down a whole lot. Look up videos of astronauts falling down on the moon. You will not be shy of material. They're falling down all over the place. They end up coming up with sort of a skipping shuffle as the best way to move in this lower gravity environment. Let's compare the rotational period. So how long does it take the moon to rotate around one time, compared to its orbital period? How long does it take for the moon to revolve once around the Earth? And astoundingly, until we actually understand the science behind it, we've covered the concept already. The orbital period is 27.3 days, its revolutionary period, and that's identical to its rotational period. So it rotates exactly once per orbit. What would life be like on the moon? Important numbers if we're trying to, say, establish a base on the moon or any sort of settlement on the moon in the future, or even just try to have our equipment survive on the moon. So the temperature fluctuation, without an atmosphere, the moon has some pretty wild temperature swings. The equatorial regions, the moon is much more reflective. Well, you can see this reflective. So the equatorial regions have an average temperature a little bit lower than we would expect for the Earth at 220 Kelvin. Although the polar regions, being the poles, are colder, an average of 130 Kelvin, that's pretty frigid. But the days are long, and without an atmosphere, it gets really, really hot. And the nights are cold, and without an atmosphere, the temperatures really plummet. So the maximum temperatures we see on the moon are about 390 Kelvin, that's 242 degrees Fahrenheit. That's hard to survive. Even for electronics and equipment. So you have to make sure that you protect against temperatures that high. And it gets as cold as 100 Kelvin, minus 280 degrees Fahrenheit. So huge temperature swings. And there's no atmosphere really to regulate the temperature. So you see these wild swings. As I was just saying, the moon has no atmosphere. Important thing to know, which celestial bodies, so which planets mostly have atmospheres and which don't. Another important thing to know, the moon is a pretty small baked potato. Let's go ahead and look. It's 27% the radius of the Earth. It is 1/8 the mass of the Earth. That does not meet our requirements for a planetary dynamo, so we don't expect it to have a magnetic field, and we don't measure a magnetic field. I always like to show size comparisons as well. So here is the size of the moon compared to the size of the Earth. This is 1/8. Or sorry, no, that's 1/8 the mass. That is 0.27 the radius. So we could fit about 4 of these side by side. And in this video, I really want to talk about an interesting fact, the fact that we always see the same face of the moon. Sure, we go through the entire cycle of phases from new to full, back to new through our waxing and then our waning. But if you look, we're just seeing different amounts of the same face of the moon illuminated. You still have the same patterns. Here's these dark spots, and they're always in the same location over the entire lunar cycle. Why is it that we always see the same side of the moon? And we never saw the other side of the moon until the spacefaring era, Apollo 8, whenever astronauts first went to and looped around the moon, we had never seen the far side of the moon. So why do we always see the same face? And since we always do see the same face, we can name the sides of the moon. The side that faces the Earth, that's nearest to the Earth, we call the lunar near side. The side that's farthest away from the Earth, the side that we never see, we call that the lunar far side. And really, it wasn't until the 1960s that we saw the other side. So really, we only get to look at about 50% of the lunar surface. Although we get to see a little bit more, the moon's orbit's not perfectly elliptical, which means every once in a while we get to peek around the edges a little bit. So we can see about 57% of the moon's surface over an entire lunar cycle. This sort of wobbling back and forth that we see due to the elliptical orbit is called lunar libration. I have an animated GIF of that in the supplemental slides, so go have a look after you're done watching this video. But I want to talk to you, why do we always see the same face of the moon? How does this relate to something that we've already been talking about, some fundamental concept in astronomy? So the easiest answer is, if we want to see the same face of the moon, if we always want to see the near side of the moon, all we got to do is make sure the near side is always pointed at the Earth. And then it doesn't matter, we're always seeing the near side. So that's our easy way of answering it. The more detailed way is the near side is always going to be pointed towards the Earth if the orbital period matches the rotational period. And that's what we saw with the moon data, that the moon spins around once and every 27.3 days, and its orbital period is exactly once every 27.3 days. So the moon's rotational period equals its orbital period. When you have this arrangement, that the rotational period equals the orbital period, we say that the moon has a synchronous orbit. And it would be the same for other celestial bodies where their rotational period matches their orbital period. They have synchronous orbits. So a moon or a day on the moon lasts 2 Earth weeks of daylight, and they have 2 Earth weeks of darkness, allowing for those huge temperature variations. Now I want to actually try to demonstrate this. So I'm going to go ahead and pick up my computer. And my face is going to be the moon, and I want you to always see the same face of the moon. I want you to always see my face, never the back of my head. So I'm going to rotate my computer around 360 degrees. But whenever I do that, I am going to walk around my computer, almost like strafing in a video game. So I'm gonna try to hold my computer still and make it do the rotating while I do the revolving. Remember, my face is the face of the moon. So I'm just rotating my computer, and as I rotate my computer, I am walking a circle around it so that if I rotate exactly one time, notice that you can see Jupiter in the background. So in one full cycle around, I spun around exactly one time, and my computer spun around exactly one time. I perfectly strafed around my computer, keeping my face always pointed at the camera. So in that case, my orbital period, walking around my computer, matched my rotational period, how long it took me to spin around exactly once. And the net result is you always saw my face. You always saw the same side of the moon. What actually creates this? Why is it that the orbital period equals rotational period? Things like that don't just happen by nature. Such a nice match of 1-to-1. Anytime we have ratios that work out really, really, really nicely, something must have forced that situation. What was doing the forcing? Tidal locking, that same process that's slowing down Earth's rotation. The fact that Earth has a tidal bulge that's getting ahead of the moon and the moon is trying to pull it back, slowing down Earth's rotation. And as the Earth's tidal bulge rotates ahead, it pulls the moon forward in its orbit, causing the moon to spiral away. That tidal locking process, that's already played out for the moon. And if we think about it, the moon is much less massive than the Earth. It's an eighth the mass, which means that it has less momentum. It's easier to slow down things that have less mass. The Earth also has more mass than the moon, meaning that the tidal force of the Earth acting on the moon is a lot stronger. The tides pulled on the moon from the Earth are pretty large. So just like the tidal bulge gets pulled on the Earth, it gets pulled on the moon. So the moon is not spherical, it's a oblate spheroid. It has a permanent shape of the tidal bulge, but it's just moving rock, so it's really kind of hard to see. It's not very unround, but we have the tidal bulge. And in the past, the moon certainly rotated faster than its orbital period, but then its tidal bulge would rotate ahead and the Earth would pull it back. And that process would keep on going, slowing down the moon's rotation until its natural consequence end, where the tidal bulge would always be pointed in the direction of the Earth, so that as it rotates once, it keeps the tidal bulge always pointed in the same direction. So the tidal locking process will eventually reach its ultimate conclusion when the orbital period matches the rotational period. And at that point, we would say that the moon is tidally locked to the Earth. The thing that was forcing this to happen was the tidal interactions, the tidal locking process, which gave us so that we always have the tidal bulge oriented in the same direction towards the Earth. We always see the same face of the moon, and the orbital period matches the rotational period. That's all I have for this video. I'll see you in the last video of the day, where we'll actually talk about the surface of the moon. Thanks for tuning in.